All right, let's start. Do you have any questions? Okay. All right, so we're done with chapter 1 of the textbook, which, right, is just some basic probability review. Now, I mean, chapter 2 and 3 are still probabilities, so, but let's kind of write down, right, sort of the highlights, right, of chapter 1. So, I guess chapter 1, right? Basically, again, it's basic probability, nothing more than that. It tells that, I mean, the things that we looked at were, right, the inclusion, exclusion formula, and conditioning, right? And so I guess, as I mentioned, right, both of these, again, not the only reason why we study these tools, they somehow, right, have to do with looking at the joint, right, looking at the probability of the intersection. They provide us different ways to calculate, right, the probability of the intersection. And we've looked at the inclusion-exclusion formula a lot, right, for the Hertz problem, so I won't repeat that. But let me just say, right, for example, in the Hertz problem, where, right, let's say we looked at probability of, let's say, EIEJ, right, where EI, right, is the event that the ith man gets his right hat, right? So here, right, remember, we got the answer to be like this, right? Which is because, sorry, n minus 2 factorial, right? And this is done by counting, right, via counting, right? Because basically we just list out, okay, out of n positions, we have two positions that are fixed, right? Namely the ith and the jth positions, where, right, the hats are correct, and then we permute the remaining positions. Now I want to show you, right? So well, first of all, right, notice this is exactly a joint, right? This is an intersection probability. So of course we did it by counting, but we can also do it by conditioning as follows. Right? And how do we do this? Well, of course, right, probability of one man getting his right hat is 1 over n. Now, what about this? Remember, right, I said conditioning gives you a different way to look at things, or more information, if you will. conditioning on EI means you know that the ith man, right, already gets his right hat. So, right, the ith person, right, the ith hat is already there. It's correct. So if the ith person already gets his right hat, then the jth person getting his right hat, right, given that the ith position is already correct, clearly must be 1 over n minus 1, right? Because this is already matched up. So we only have n minus 1 positions left, right? Out of which or n minus 1 hat left, right? And then of course, right, everything being equal, equally likely, the j person getting his right hat is 1 over n minus 1. Of course, right, you see that this is exactly that number as well. So they are the same answer. But these are arrived at, right, using different ways. This is counting, and this is by condition. So again, right, just to show you that there are many ways to arrive at one calculation, right? There are tools. How we use them is exactly, I guess, just up to us. But the more tools we have, like the more ways we can approach a problem with. All right, any question about this? All right. So two more things, right, about conditioning. That kind of like related to conditioning that we should remember because they will be used a lot in the future. The first thing is the law of total probability, right, as I mentioned last time, which says that if you have E1, E2, etc., right, you can stop at En or you can just keep going to infinity, it doesn't matter, as a partition, right, of the sample space, then the probability of an event will be the sum of that event, right? Probability of that event with intersecting with all the EIs. And then you can condition on each of the EI to get the following. Like that, right? And it's this form that tends to be used a lot, okay, in the future. And again, the meaning is, right, instead of calculating the probability of an event, we calculate the probability of that event condition on, right, one of the possibilities. Depending how we decide to, dissect, right, the universe. Depends on how we decide to partition the universe, right? The EIs are our choices, right? We choose to see that these are the only possibilities that the universe can happen. Like on the first step, these are only so many ways you can take, right? These are so many possibilities you can take on the first step. Then the probability of the future is exactly the probability of the future conditioned on what kind of first step you took times the probability of that first step, right? And taking that way. The second thing is a problem, right, from the text, which is kind of, well, I don't know what the name of that is, right? But basically, it sort of generalizes, right, this principle right here. So instead of taking the intersection of one event, now it looks at the intersection of n events, right? And it just basically now hold on, let me try to see, right, where do we want to, I guess, let's do it this way, right? You start from the end, you condition all previous events, and then you have this condition on all previous events, so on and so forth, right? Until you have this. Okay, like that. All right. And so again, this law, as you can see, I wrote it down sort of using my intuition, okay, using what I memorized. But memories, can be faulty, right? So it doesn't hurt to kind of check real quick that the formula we wrote down is correct. Well, for example, right, the top right there is exactly E1 up to En intersection divided by, right, E1 up to En minus 1, right? And then you have E1 up to En minus 1 intersection divided by E1, En minus 2, right? And so these two cancel. The next term, right, will be up to En minus 2, and then up to En minus 3, right? Because the next term would be En minus 2 condition on everything up to En minus 3. And so we'll cancel, right? So on and so forth. And you see things will keep canceling until we get P of E2, E1 over PE1, right, times PE1 like that. And so again, right, things cancel. And then the only thing remains is this term, right? So the meaning, right, of course, is that is a generalization of this principle, right? But to n steps. So the probability that you take the path, right? Now think of the n right here as time, okay? The probability that you take a path, right, going through n steps is exactly how you ended up on the last step, condition on all previous steps, and how you ended up on the, next to last step, right, n minus 1, condition on the previous one, so on and so forth, right? And until, right, of course, the probability of how you take the first step. So this, right, will have relevance whenever you deal with something that progresses in time, which is, of course, right, stochastic processes, discrete time, right, 1, 2, and etc. Last but not least is what I call, right, further conditioning. Where you can think of something like this, right? Probability of E1 condition E2 is probability of E1 condition E2 E3 times PE3 condition E2 plus P of E1 condition on E2 E3 complement probability E3 complement condition E2. All right. So this also can be viewed as a generalization of the law of total probability, but sort of like condition on E2, right? So how it works, right, is that, remember, so let me write down the reference for you, right, in terms of the problem. This right here, right, is number 23 in chapter 1. And then this right here is number 47. And the point, right, is that, well, in number 47, right, the textbook tells you to check that when you condition on an event, then this acts like a probability, okay, with the universe being E2. Therefore, right, being the universe being E2 now, if you further condition on E3, then you just do it like the law of total probability, like this, right? But now instead of condition on E3 and E3 complement, right? So okay, let me write like here, right? In the law of total probability here, right? The easiest implementation of the law of total probability is when you have two events, right? E1 and E and E complement, because they will form a partition of the sample space. Then the probability of an event will be probability of an event, condition on E times PE plus probability of an event, condition E complement times PE complement. Okay, like that. So you see, this is sort of like a generalization of that, if you will. So instead of, right, just having PF, now you have PF condition on E2, let's say. And so now, right, instead of condition on E2 only, right, now you got further condition on E3. So, right, that's this. And then multiply with instead of multiply with P of E3, multiply PE3 condition E2. All right. So now here, your universe is the original universe omega. Here, your universe, right, has been changed to conditioning on E2. All right. So these are, right, the highlights of chapter 1. As you can see, right, there are already a lot, especially this, I would say, right, new laws that you may not have used. You might have seen some of it, but you may have used, right, in probability. But as conditioning being the backbone, or being sort of like the tool that stochastic processes is built on, then these laws, right, will be used over and over again when we study stochastic processes. And so you should, or you must be very fluent, right, with these laws, because otherwise, right, when we use them, you will not be able to use them correctly, or you will not understand what they mean, etc. Right, which all of which means that you will have a hard time following what we be doing. Okay. Any question before we continue? All right, so now let's move on to chapter 2. And chapter 2 is titled Random Variables. Well, so make no mistake, right? Chapter 2 is much bigger than chapter 1, let's say. And it's it's about a lot, it's a lot. It has a lot of materials, right, on random variables. So the first thing, okay, that we want to talk about is just a basic review, right, of random variables. So 2.1 is an intro, which we'll skip because I don't know. I mean, I would expect you to know what a random variable is. If you don't, well, that's not a good sign. Well, and also we'll be talking about random variable a lot anyway, right? So we're not gonna have to introduce you to random variable. So 2.2 and 2.3 are about discrete and continuous random variables. Okay, and as you can see, right, these are just basically, you know what? Let me take it slow. Let's just do 2.2, right? Discrete random variables. So the point, right, is that The one thing I can say, right, is that random variable, well, I say skip random variable, but random variables are, you can think of them as basic model, right, of certain things. Well, you should know something like Bernoulli, right? Binomial, I think in the first class, someone mentioned geometric random variable, right? These are all discrete random variables, and they're supposed to model something. Um, the reason, right, why they're useful, right? I mean, so how to say this? So when we say discrete random variables, we mean all kinds of discrete random variables. But of course, right, from any basic probability class, you would learn some basic discrete random variables, okay? So these are really basic models. So any random variables is a model of something, I guess. But these are sort of like the models that people always carry around, and they would readily apply, right, these models to a problem that they see that somehow, has that kind of phenomenon, right, as captured by these basic discrete random variables. The point, right, is that you have to be very, very familiar with these basic random variables. So familiar that you would know, let's say, their probability distribution, you would know their mean, you would know their variance, right? Right on top of your head, like you memorize them. Again, right? I mean, this is like because you work in this area, let's say. And if you don't have this memorized, then I don't know, you're just gonna have it's like you have to know the derivative of basic functions. Because if you don't, then you're gonna have a hard time doing calculus. All right, so without further ado, let us kind of see what you remember, right, from your probability course. So basically list out, right? So the name of the random variable, the probability distribution function. You know what? Let's start slow. With any random variable, as you know, I will be asking for something called a support. Basically, the support of a random variable is the range of values, right? Where the random variable takes, let's say, non-zero probability or non-zero PDF, right? Density. So that's basically what range of values that random variable takes. A support, so now the probability distribution function, in which case, the abbreviation is still PDF, but usually PDF is reserved for probability density function. So let's just write the whole thing out. Expectation and variance. All right. So I believe there are like about, right, 5 or 6 basic discrete random variables that you should know about from probabilities. See what you know about what you know, and then we're going to list them out. Now, of course, right, everyone's list can be slightly different because some people might have something then like certain things like the I don't know the gamma, right, the beta. These are continuous random variables that technically speaking are very, very popular random variables. Um, they sort of show up more on the statistics side. So what I'm trying to say is like, right, of course, the word basic here is also sort of subjective, right? Depends on what people work on. So this list may be different for different people, but everyone should kind of have similar list, right? A core list that they all agree upon, for example. All right. So let's see. Can anyone tell me, right, one of the random variable here and the relevant information? What discrete random variable do you know? And what are the information about this random variable? Nothing? Okay. So how about we start with the most basic one, which is the Bernoulli. So if we say a random variable is a Bernoulli random variable, with parameter p, right? What do we mean by that? We mean a random variable, right? That takes value 0 or 1, right? The distribution function will be that probability x equals to 1 is equal to p. Expectation is p, variance is p1 minus p, right? Well, the next one on the list is let's say a binomial NP. Well, for binomial NP, right? What's the support? What kind of values can a binomial take? From 0, 1 up to n, right? And the probability distribution will be n choose k, p to the k, 1 minus p raised to n minus k, right? Expectation is n times p, variance is np 1 minus p, right? And well, what's the next one? What's another example of a discrete random variable? Well, how about the geometric? right? So what is the geometric random variable? Well, geometric P, right? A geometric random variable describes the experiment, right, where you keep performing, right, trials with success probability P until you see the first success, right? And the geometric random variable records the number of trials, right, until the first success. So the values that a geometric random variable can take is 1, 2, etc., right? And it has no upper kind of bound, because you can keep on, right? You don't have an upper bound on the number of failed trials, right? Before you can have a first success. So here, probability, right, that the geometric take on value k will be p, right, to the 1 minus p to the k minus 1 times p, right? So if your first success, right, happens on the kth trial, then the previous k minus 1 trials must be failure, and then the last trial, right, is a success. Expectation here is 1 over p. What about the variance of a geometric random variable? All right, I'll leave that as a question mark. We will be doing problem where we work out, right, both this expression. But so I'll let you kind of figure out or find out, right, what's the variance of a geometric random variable. Next one is the Poisson parameter lambda, right? So a Poisson random variable basically models what? A Poisson random variable models the let's say the number of events, right? Number of let's say, yeah, Poisson random variable lambda, right, is the number of is the rate of arrival, right? So basically, Poisson random variable measures, well, it's associated with rare events, and we'll say why that's true, but it's not really. So that's one interpretation. But basically, it looks at, right, the number of arrivals during a period of time, right, with the rate of arrival lambda. So lambda here is a rate of arrival. Okay. So for example, if you look at the number of earthquakes, okay, during a year, then that's going to be a Poisson, that can be modeled, right, using a Poisson random variable, because you can have the average rate of earthquake per year is so and so, right? You can also look at the number of people arriving at a, let's say, a store, right, during an hour. That can be modeled as a Poisson random variable, right, with a certain rate. So the values, right, that the Poisson random variable can take will be 0, because you can have 0 arrival during a certain time interval, 1, 2, etc., right? So notice that here, right, the Poisson random variable can take a value 0. Geometric random variable, by definition, right, will not take value 0. The lowest value it can take is 1. The probability distribution function will be e to minus lambda, lambda to k over k factorial. Expectation is lambda. what were the variance? What's the variance of a Poisson random variable?
Is it 1 over lambda?
No. I think you're thinking of the exponential. Poisson, the variance is also lambda. Okay. So the Poisson, the expectation, and variance are the same. Again, you should think about why, or you should try to have an intuition on why. All right. Anything else to add to the list? Well, one random variable that you tend to study in probability is the hypergeometric. I don't think it will show up a lot in this class, so I'm just gonna say very briefly, right, about it, and we won't list out everything. But the hypergeometric is basically about, something like selection, right, without replacement, right? Let's say among two groups, right? Of size, let's say k and n minus k, right? So basically you have, let's say, k red balls and n minus k blue balls, right? And then your sample size can be something like r, right? So you select r objects, okay, without replacement among the two groups, right? So basically you select r balls out of n balls, right? Among which k is red, n minus k is blue. And your question is like, among these r objects, how many of them, right, is blue? Things like that. So how many of them belongs to, let's say, the first group, right? So clearly the support, right, the value, um, you know, you can take sort of depends on R and K, right? So the number of blue balls that can show up in the selection will be the minimum, right, of R and K. So of course the smallest one can be 0, but the biggest one here sort of depends on, right? Because for example, if you have only 5 blue balls, but your selection is 6, right? You select 6 objects total, then clearly the maximum number of blue balls you can get in your selection is only 5 anyway, right? On the other hand, if you have 5 blue balls and you only select 3 objects out of the whole thing, then the maximum number of blue balls is 3, right? Things like that. The probability distribution function will be what? So the probability of x equals to, so I only use k here, right, for the group size. So, you know what? Let me change this to what? So what's another letter for the group size? Let's say m, right? Like that. So probability x equals to k will be, well, the total number of possibilities is n choose r, right? Out of n objects total, you choose R objects, right? Now, the numerator, so you want out of R objects, you want K objects. Sorry, out of M objects, right? Out of the first group, right, you want K objects to be in the first group, which leaves you with the remaining ones must be from the second group. Okay. So it's a combinatorics, right, kind of calculation, has to do with selection without replacement. It shows up once in a while. So we should know it, but when it comes to it, we're probably just gonna do a combinatorics calculation. The thing to note, right, about the hypergeometric is the expectation. Does anyone know what the expectation of a hypergeometric is? If you have, let's say, M blue balls, right, within N objects, N balls total, and let's say you select 4 balls out of 10 balls, right? I don't know, let's say you select 6 balls, right, out of 10 balls, 4 which is blue. How many blue balls do you expect in your sample? Well, the answer here is the sample size, which is R, times the rate, which is M over N. Okay, that's the expectation of a hypergeometric. And this is something worth remembering, because if you do know the expectation formula, right? Let's write down real quick. What is the expectation formula of a random variable when it's discrete? For a discrete random variable, right? The expectation will be the sum over all values it can take times the probability it takes on that value, right? So notice that, for example, by listing out the expectation here, these are some, let's say, not trivial calculations. For example, right, we assert that N times P, right, the expectation of the binomial is the sum K from 0 to N of K times N choose K, P to the K, 1 minus P to the N minus K. Now, I would strongly challenge anyone who thinks that the binomial distribution is easy to prove this identity. All right. This is not, I mean, it's not that hard if you know where to look and what to do with it. But this is not a trivial identity to just say that, yeah, obviously that's true. Okay. Another example, of course, is like, say, the geometric, right? With the geometric, it says that 1 over P is the sum, okay, from 1 to infinity of K, P to K, sorry. 1 minus P to the K minus 1 times P, okay? Again, another non-trivial identity, I think. So on and so forth, right? And this is the reason why you want to memorize this result, because you're not going to be able to work out this expression by definition of an expectation, you know, let's say on the exam or whatever, okay? So same thing here with the hypergeometric. if you look at the probability distribution formula and you sum, right, overall possibilities, I very much doubt that you can come up with the answer like this. And surprise is actually I think I know how to work out all the identities of the other random variables. They're not trivial, but they're not that hard. I don't think I know the direct way to work out the expectation of. I mean, I do know some way to argue out why this is true, but not through a direct calculation like this. Okay. So again, right, yet another reason why we want to memorize this. The variance of a hypergeometric, I think, is not something no one really memorizes unless they have to work with the hypergeometric a lot. So let's leave that aside. Okay. What else? Is there any other random variable we should list for discrete random variables? Well, there's one thing that tends to show up, which is the negative binomial. All right. So the negative binomial, I think, has some relationship with the binomial, of course, but I don't remember what the relationship is exactly. I mean, I'll know them when I see them. It actually has a direct connection to the geometric, actually. Okay. So the negative binomial, I think, would have two parameters attached to it, n and p, just like the geometric. So actually, the geometric random variable can be viewed as a have negative binomial 1p. So clearly, right, n here represents a number of successes you're looking for. So basically, for the negative binomial, you perform trials with success probability p until you see n successes. All right? Until you see n successes. So clearly then, right, the number of trials, so the support, right, which is the number of trials you have to do to get n successes, is n plus 1, right, n plus 2, etc., so on and so forth, right? So basically, you have to perform at least n trials to see n successes, and there's no upper bound on the number of trials you can do. Here, probably x equals to k will be, right, you must have, so here, all right, maybe let me pause, right? Anyone care to say what the distribution for the negative binomial is? In other words, right, for a negative binomial, what's the probability x equals to k? You take k trials to get n successes, to see the first n successes. All right, so you perform k trials, right? And then you do know that the last trial must be a success, because, right, you have seen n successes with k trials. You also know then, right, that out of the previous ones, k minus 1 trials, there must be n minus 1 successes, right? Because that's the only reason why you see the first n success on the kth trial. So therefore, the calculation is out of the previous n minus 1 trials, you try to select out of the previous k minus 1 trials, You select n minus 1 successes. Okay, select a position for n minus 1 successes. And then, right, the last one must be success. And then the probability, right, for that to happen is still 1 minus p, right, to the, well, so how many failures do you have, right? You have n minus k minus n failures. And then you have n successes. All right, any question about this? Anyone care to say or to guess what the expectation of the negative binomial is? So just like the geometric, right? The expectation is 1 over p. So the geometric is number of trials until you see a first success. So number of trials until you see n successes will be n over p, okay? So n over p will be the expectation of a negative binomial. The variance we'll just leave blank for now. We'll fill that in later. So, right, as you can see, there's 1, 2, 3, 4, with the Bernoulli, right? 5. By the way, the Bernoulli has another name. It's called the indicator function, right? Because it sort of like indicates whenever something is a success or a failure. So it's an indicator, random variable or indicator function, all right? So 1, 2, 3, 4, 5. Let's say the hypergeometric can be counted as a 6 or not. This 5 will be seen a lot in this class. So you should be sort of very, very familiar with them so that, you know, you can operate with them well. All right, any question about this? Okay, so maybe next thing to do is to mention, right, the relationship among these random variables and sort of along the way, right, review certain kind of probability concept that will be relevant. So I guess we mentioned expectation, right, of a random variable, discrete random variable. What about variance? So variance of the random variable, right, by definition will be the expectation of, let's say, x minus e of x, right, squared. So it's the mean square error, right, of x away from its average. But if you expand the expression, you can also end up with this, right? So one of the expression, let's say this one, is more like a conceptual definition, right? It's the mean square error of the random variable away from the mean, right? This is more of a calculation formula, like people tend to calculate the variance this way. So, well, let me say, right, that I guess students, right, tend to confuse this a lot when they perform variance calculation. What else do I want to say here, right? So the rules that you should remember about expectation and variance is the following, right? Expectation is linear. In other words, if you have expectation of a sum of a random variable, sum of random variables, then it's going to be the same as the sum of the expectation of these random variables, right? So it's linear. On the other hand, right, the variance is not, right, linear, generally. In other words, the variance of a sum of random variables is generally not the sum of the variances. So let's see if we know, right, the true formula here. Write down the correct formula for variance of a sum of random variables. All right, so what's the formula here for variance of the sum? So the variance of the sum of random variables will be the sum of the variances plus, right, the covariances. So here, right, is basically symmetric. So you can have x1, x2, x2, x1. So another way you will see this being written is twice, right? But if you do two, then it's just I less than j. Like that, okay? Now, I hope, right, the covariance is not a strange object, but maybe let's just make sure we write down. What's the covariance of two random variables? Well, again, right, just like variance, it has two definitions. One is kind of generic. Sorry, one is kind of conceptual. So it's sort of like a cross product, right? So not cross product, but like, yeah. So the interaction, right, the cross between the xi and xj, normalizing, right, using this expectation. So that's the conceptual definition. The way people calculate them is using this, right? Again, I hope that it's very easy for you to move from here to here, right? Using exactly linearity of expectation, right? Same as it's going to be I hope it's going to be very easy for you to move from here to here, right? Again, using linearity of expectation. But here, right, we note that the covariance of two random variables is going to be exactly 0, right? Only if xi and xj are independent. So in other words, right, if two random variables are independent, then the covariance is going to be equal to 0. But not the other way, right? Covariance equal to 0 does not necessarily imply that two random variables are independent. And so, well, right, you see then the variance, right, is equal to the variance of a sum is equal to sum of the variances plus the covariances. So it's equal to a sum only, right? I mean, technically speaking, right, only when the random variables have zero correlation, right? Now, of course, a particular case that tends to happen is the random variables are mutually independent. If the random variables are independent, then the variance of the sum is the sum of the variances, right? But that's not true in general. So let's write that down. And the variance of the sum, right, will be sum of the variances only if, right, covariance xi is xj is equal to 0. In particular, if they're independent. All right. Are we okay? Any question with this? So, yeah. So what we're saying here, right, about variance and expectation, all these things, kind of, move to the topics of section 2.4, 2.5. 2.3 is about the listing of all basic random variables, but it doesn't matter, right? We can just kind of talk about all these topics together. So we're gonna move to 2.4, 2.5 and talk about certain problems there more specifically. But the concepts here, right, is if you care to read the textbook, it's gonna be in sections 2.4, 2.5. Right, so now let's move back to what we tried to discuss, which is the relationship, okay, of these random variables. I mean, not all of them have relationships with one another, but they do have some relationships, some well-known, some subtle, right? And you want to know them all, I hope, to be able to appreciate this model more. So relationships. Okay. So the first relationship that we should know, and it's sort of like the common theme for this class, at least in a lot of problems, is that, right, you can sum. So for example, right, you have x1 to xn, IID Bernoulli. Okay. So IID here, right, means independent and identically distributed. the second part is sort of like redundant if you say that they're all Bernoulli, but you know, it's sort of like conventional, right? That we just list out IID together. So basically we have independent trials, right? N trials. Each of them is a success with probability P. So if you sum these random variables up, all right, and let's say you call that random variable X. So this happens a lot in a class like this or in stochastic process or whatever in general. We tend to sum random variables a lot, okay? Then this will have what kind of distribution? If you sum up Bernoulli random variables, what do you get? Well, you will get a binomial. Okay. Well, it's just sort of clear that it works that way. Because what is a binomial? The binomial random variable, right, is a random variable that describes number of successes in n independent trials. Each of them have success probability P. So if you look at each individual trial, and right, you sum the number of total number of successes, of course you get right number of successes. So that's just argument by, let's say, conceptual, right, by understanding the model. We're gonna show you another way to do so via the moment generating function, right? Which is yet another very important concept here. But right now, this is just by, you know, the way we understand the model, right, of the random variable. So why is this useful? It's useful, for example, right, because expectation of a Bernoulli random variable is very easy to calculate, right? It's basically 0 times 1 minus p plus 1 times p, so it's p, right? The variance of a Bernoulli is also very easy to calculate because basically it's going to be what? Expectation of the square minus the square of the expectation. And, right, expectation of the square is clearly just 1 square times p, right? Because 0, right? Not going to contribute to the expectation. Subtracting, right, p square, because that's the expectation square. P minus p square is, of course, p times 1 minus p. Okay. So, but when it comes to the expectation and the variance of a binomial, as I mentioned, right, the formula becomes suddenly much more complex because, again, I challenge you to somehow show me that this is equal to n times p. Or maybe I'm exaggerating the difficulty here. Maybe it's easy. Can anyone show me why this is true? Well, if not, right, then I hope you appreciate then, right, the following way. Well, it's not clear how to calculate expectation of x directly. Definition, okay? However, knowing that x can be written as a sum allows us to use the linearity of expectation and each of these is P, so the expectation is N times P. Not only that, right? If expectation is not easy to calculate directly via definition, then you can bet that variance is along the same way, if not harder, because variance, right, is expectation of square minus expectation. The definition or the calculation will be technically complex, all right, complicated. So these are both not easy to calculate by definition. On the other hand, right, the xi's here are independent, and if random variables are independent, then the variance of the sum is the sum of the variances. So we can use the same trick to say this is N P 1 minus P, which is exactly, right, what the formula said. All right. So what I just told you is the relationship between the Bernoulli and the binomial, okay, which is very, very well known. And it's actually not only valid, let's say this approach is not only valid for this particular pair, it's valid for many, many, many cases, right? This is an example of something we call counting by indicator function. So basically, to operate or to work with a complex random variable, you break it down to smaller random variables that can be more easily handled in terms of calculation. And then you use, let's say, independence or linearity of expectation to calculate the original expectation, things like that, all right? And trust me on this, this technique will be very, very common in chapter 2 and beyond. So you should master this as soon as possible. All right, any question on this? Okay. So what's another pair, right, in this list that can benefit from the same treatment? Well, as you can see, right, another one that can benefit from the same treatment is a negative binomial and the geometric. All right, because if the geometric random variable is the number of trials until you see the first success, then clearly, right, the number of trials until you see n successes is just the independent sum of a geometric, right? Because you just wait for the first success, and you wait for the second success, and you wait for the third success, so on and so forth, right? So similarly, if you have x1 up to xn, IID, geometric P, then the sum of the xi one to n, right? If you call this x, then x will have negative binomial NP distribution. Okay. So again, the significance of this, at least right from the point of view of calculation of the expectation and the variances, is that expectation of the negative binomial will be the expectation of the sum, which is a sum of the expectation, which is n times, right, expectation of one random variable because they're all the same. And that's going to be 1 over p, right? So n over p. The variance works in a similar way. And here I stop because, I mean, I do not remember, right, what the variance of a geometric P is. So, but if you do know it, then whatever this number is, you multiply by that by n, you will get the variance of a negative binomial in P. That's how it works. Okay, any question? So, the next thing, right, will be, so among these random variables, right? So we talked about the connection between Bernoulli and binomial, the geometric with the negative binomial. Now, what about the Poisson random variable? So Poisson, I guess, has some connection with the exponential, but that connection is a little bit, let's say, advanced. Well, we'll talk about it when the time comes. But for now, right, the Poisson will have a connection with the binomial, all right, as a limiting distribution, in which case it explains why Poisson is used as a model for rare event. Okay, so here's how it works. Suppose you have x as a binomial NP random variable, and suppose that n is large. Okay, as very typical with binomial random variable, you could, a lot of times you have a lot of trials, right? A lot number of trials. So that's what we mean by n goes to infinity. But that's not enough. You also have p going to 0. So that's the second important thing, okay? P going to 0. So basically, okay, but I guess one more thing, in such a way that n times p, this product, right, is fixed. It's always lambda. So what are we talking about? So this exactly right here is a description of what we mean by rare event. Okay. So what you're looking at, right, the description of, let's say, 1,000 or so, right? When n equals to 1,000, yeah, kind of like it's going to infinity. Let's say you have 1,000 trials, right? Each of them has only success of 1%, or, you know, if you like, success of 0.001, right? Something like that. So n goes to infinity, p goes to 0. But, right, what's n times p? N times p, right, is, if you remember, the expectation of x. So n times p here is sort of like the average number of successes, right? So basically, you have the number of trials being very large, the success of each trial, individual trials, very small, but somehow, right, the average number of success is a constant that you know. Okay. What's some example of this? Number of earthquakes. Okay. Earthquake is a relatively rare event, right? And here you can think of it as like number of days, a number of hours. So every hour, right? Even if you live in like an earthquake area, right, like California, in an hour you don't expect to have any earthquake, right? I mean, in an hour. So basically, but as the hours accumulate, right? I mean, sort of like in a year in which there are a lot of hours, right? Then there's sort of like some fixed. So the probability of an earthquake happening in any particular hour is small. But if you accumulate it, right, then you expect certain kind of fixed number of earthquake, let's say per year, 2 earthquake per year, right? Another example is like you read, you know, a book, right? And then on each page, right, there's so many words. There's a lot of words. So that's N here represent number of words. P here would represent, let's say, the probability of a word is a typo, right? So when you read along each word, I mean, there's a small probability, let's hope, right, that a word is a typo. On the other hand, the average number of typos, let's say per page, which is like so many words, is a fixed number, right? Let's say you expect to have 1 typo per page, something like that. So this kind of try to describe that scenario. So, but if this is true, then you can say that X is approximately a Poisson random variable. So the word approximating here is a vague word because I'm not really, well, I'm going to tell you now, right? But approximately here is a word that means different things when you do probability theory. Here, what we mean is approximately by distribution. So probably X equals to K will converge to e to minus lambda, lambda to K over K factorial, right? Which is the Poisson lambda distribution as n goes to infinity. Okay. I guess as n goes to infinity, P goes to 0 and P stay lambda like that. Okay. So again, right, notice that first of all, probably X equals to K here, X being a binomial random variable, is n choose K, right? P to the K, 1 minus P raised to n minus K. So this expression right here, when n is small, sorry, when n is large, P is small, NP is equal to lambda, converges to this expression. Again, right, this is probably a significant thing, as in, well, I mean, not significant, but let's say deep, in the sense that I don't think, right, again, I would challenge anyone to prove that this converges to that when this is true, right? It's not easy. But let's set that aside. So here is the importance of knowing this. The first thing, of course, is it explains why, right? People keep telling you that Poisson, right, is used to model rare events, right? This is the reason why. Second, it's probably explain the draw of lambda in a Poisson random variable, right? It models the average number of successes, right? That's why lambda is called the average number of arrivals because of that. Third, right, is exactly the connection between expectation and variance of a Poisson. So expectation of X, right? If you look at expectation of this random variable, it is n times P, right? But we know n times P is lambda, so expectation of X is lambda. So far, right, consistent in the sense that we treat X both as a binomial random variable as a Poisson random variable, right? Because X is also approximately Poisson. So this works. What about the variance of X? The variance of X, right, is n times P1 minus P, right? But now what scenario are we in? We're in the scenario where P goes to 0, right? N goes to infinity, and P equals to lambda. So this is lambda. But what about 1 minus P? 1 minus P, right? As P goes to 0, 1 minus P goes to 1. So this also is lambda. And this exactly explains why, I mean, well, not explain exactly, but this kind of gives you another way to see why Poisson has variance equal to expectation, right? Expectation of Poisson is lambda, variance of Poisson is also lambda. Any question? Okay. So let me give you a caution here. And again, right, the caution is because, well, in probability, there are many results. You must be careful what you're talking about. You should have heard, or you might have heard, or well, should have, of something called the, so what I was telling you about here, right? This is one way to say it, but a lot of times people would call this the Poisson approximation of the binomial. Okay, that's what you would call it. Now, obviously, you should have heard of something called the normal approximation of the binomial, right? And this should make you wonder if, right, they're the same thing, if they're different, or if what's going on here. And actually, it should make you feel weird because Poisson is a discrete random variable. Normal is a continuous random variable, and I guess they have nothing in common. So what's going on here? What's going on here is that, yes, these are both something that are valid for the binomial. So you can do both. However, there's a crucial difference between the two. The crucial difference is the normal approximation for the binomial works for binomial NP when n goes to infinity, but p gets fixed. And typically, p is a large number. Like, let me just say this, right? This notation. P is not close to 0, okay? Like P is 0.2, 0.5, that kind of thing. On the other hand, right, whenever you have a Poisson approximation for that binomial, P has to go to 0. So it has to be a rare event. It's an event with small probability. So if you ever use the Poisson approximation on a binomial where P is not close to 0, then it's not going to work, or it will work very poorly. Okay, but for normal, again, for normal, if you use the normal approximation, but P is approximately 0, then I think it will work very poorly. You'll want to use Poisson. All right, so that's the difference between the two. All right, any question? So let's do a example, right, to demonstrate, I guess, the tools which you study. So here's a quiz. Again, right, consider the hat problem. Wait, this is quiz 3, right? Yeah. So consider hat problem, right? With n people, n persons. All right. Now let x be the random variable that represents the number of men with their right hats. Okay. Find expectation of x. All right. Does anyone have an answer here? So first of all, right, let's see what we're dealing with. Well, what kind of values can x take? As a random variable, right? What kind of value can x take? So x can take value 0, 1, etc. up to n, right? Can be no man with their right hat, 1 man, n men, right, with their right hats. All right. So expectation of x, right? Let's say by definition, with a sum, right, from 0 to n. Okay. All right. Well, so the question is, how easy is this, and how easy is can we write down the calculation? Well, so first of all, right, do we know what probability of x equals to k is? Do we know what probability x equals to k is? Well, the answer is yes, right? Sort of, but it's not going to be quick to write down. If x is equal to k, that means k person getting the right hat, right? That means n minus k. Gets the wrong hats. Okay. So, well, I guess here, right, you can say it's the following, right? Suppose 1, 2, etc. up to n, right? Suppose you want to find a probability, right? Notice x is number of men with the right hat. Then x equals to 2 means exactly 2 people has the right hat. Let's say person number 1, person number n, right? So if exactly 1 and 2 people getting the right hats, then the remaining n minus 2 people must get the wrong hats. So let's n choose k here, choosing which one guessing the right hats, and the remaining must get the wrong hats. And we have worked out, right, a general expression for n people getting the wrong hats. So this is just n minus k. So it's that same expression, right? This is the hat problem, but with n minus k, right, persons. Okay. So in other words, yeah, we can write down something, but I'm not gonna go back and write down the whole expression because, well, for obvious reason, even if we plug that in, it's unclear what we're dealing with, right? Because this has a sum, has this, and has that term. Okay. So in other words, right, we can write down something, it's just unclear what that is. Sometimes it's the best you can do. In other words, that's just an expression, right? There's no easy simplification, there's no easy calculation. But on the other hand, as typical with a lot of these problems, this is not the right expression. Oh, sorry, this is not the right approach. This is not, this is unsatisfactory, right? So the right approach is to use something called the indicator function. All right. What kind of indicator? Well, notice that x is a total number of men with their right hats, right? I mean, the word total is not written there, but sort of implied. So if you go through each man and you say, let this be 1 if, sorry, xi, right? If the ith person gets their right hat. And 0, right? Otherwise, meaning the ith person getting the wrong hat. Okay, so that's the language. Or, of course, you can say, sorry, no, of course, but later on, right, we're just going to write down as a shorthand, let xi be the indicator that the ith person get the right hat. Okay. So that's it, which is kind of this, right, in the shorthand. All right, so you can see, right, if you go through each person and you count them up, you say 1 that if that person gets the right hat, 0 if not. Then if you sum this up, clearly, right, you're looking at the total number of men with the right hat. Okay, and this kind of approach is called the approach using the indicator function. Well, what's the benefit of doing so? The benefit, of course, right, is first of all, expectation of x is, right, the expectation of the sum, which is the sum of the expectation. Now, each xi is a Bernoulli random variable, right? So in other words, this should be very easy to calculate. So let's see if we can do that. All right, so in other words, tell me what this is. All right, does anyone have an answer here? So each xi, right, being the indicator function that the ith person getting the right hat. So expectation of xi, which is basically probability of xi equals to 1, right? Which is exactly a probability of the ith person getting the right hat. And the answer is 1 over n. So sum here. It's just a sum of 1 to n of that happening. So that's 1. All right, that's it. So notice that a expression, right, that is very, very complex, I guess, turns out to be just 1. And that's why the above approach is unsatisfactory, right, or not acceptable, because the real answer is actually much easier than that. Any question? All right, so the next question will be a very important problem along this way, along this kind of spirit. So it's called the coupon problem. So it says that suppose there are 25 types of coupon. And suppose each time one obtains a coupon, it is independently and equally likely to be any of the 25 types. Let X be the number of different types of coupon in a collection of 10 coupons. Find expectation of X. Okay, so that's the problem. It's called the coupon problem. Okay, because I mean, sort of refers to coupon and stuff like that. So I guess the first question is the question clear here? I mean, is it clear what they're asking you to do? Or what is it clear what X refers to? Forget, right, how to calculate it. We have a clear idea of what X is describing. All right, so what does X talk about? So 25, there are 25 types. It's not exactly the same case because I think there's are only 24 letters in the alphabet. But let's suppose that, right, the types are the letters A, B, C up to Z, right? Again, suppose that there are 25 letters here. I don't think that's the case. But, you know, let's pretend. So just to demonstrate the problem, right? So each time, right, you open up a coupon, then it can be any of this letter. That's all it's saying, right? So when you have a collection of 10 coupons, right, then clearly, for example, the first can be a B, the second can be a C, right, so on and so forth. And then so let's say the last one is E, right? But of course, right, the type can repeat itself, right? For example, you have a B here and you have a C here, and then you can have a E here. And then, you know, let's say A, B, how many already? 6, right? 7. Let's say G, A, E, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, let's throw in a B, okay? So in this case, this is a collection, right, of 10 coupons. How many different types are there? A, B, C, E, G. So 5 different types. So the keyword, right, is different. 5, right? So different. Well, an extreme case, right, is somehow in your collection you get everything of the same coupon, same type, then that's count as one, right? Different type. I mean, the word different here, I guess it's meaningless, but yeah, one type. Are we clear? So X keeps track of this number. The question is, on average, right, out of 10 coupons, how many different types can you get? All right. Anyone has any suggestion on how to do this problem? So the reason why I list this problem right after, right, the hat problem is because they're both accessible to the same technique, which is indicator function, right? So now that I tell you that, can you see what kind of indicator function should we use or must we use for this problem? What are we counting up? What are we looking at? So we should break X down into a sum of some random variables. What are they? All right. So maybe let us ask this, right? When we sum like this, the challenge with this particular problem is you can sum across the coupons from 1 to 10, or you can sum across the type from 1 to 25. Which one do we sum across? The coupon, 1 to 10, or the type, 1 to 25? Well, the answer is we sum it across the type. Okay. So what are we looking at here? We look at each type, right, from 1 to 25, and we ask if the ith type is in the coupon. Sorry, in the collection. Is that okay? So for example, right, you go through the list A. Is A in the collection? If yes, that's one type. Is B in the collection? If yes, that's 2 types. C, 3 types. D, no, so still 3. E, yes, 4th, so on and so forth. Okay? So it's clear that when we do that, this will list out all the different types in the collection. All right? So now the expectation of X will just be expectation of sum, which will be sum of the expectation. Now, what is expectation of Xi? What is it? Well, notice, right? This question is not easy to answer directly in this way because you're not asking if a card is of type A, for example, right? Because you ask if it's in the collection, all you need is at least 1 card of that type. So let's write that down, right, to make it clear. But you see, right, so you can go through each card and multiply that the probability of that card being type I or not. That's fine. But the question is how many, right? Here is at least 1. So you have to do 1, 2, 3, etc. up to 10, right? Which is the total number of cards, the maximum total number of cards being in type I, which is, right, you see is kind of tedious. So we will do it through the complement where we do 1 minus, right? The probability that type I not, right, in the collection, which means, right, that you go through each card in the collection and say that is this not of type I. The probability of that clearly is 24 over 25 raised to the 10th power, right? So the final answer then, right, is going to be this, but each of them being the same number, right? So it's going to be 25 times like that. All right, any question about this? All right, if not, then I think let's stop here. I will post the homework for today, and I'll see you next Monday.
Wait, Professor, can you go back to the slides for a second?
All right. Mm-hmm.
Thank you.
Yeah. We're good?